All right. New chapter. Building on what we've seen from ODEs and series solutions. Today, so I'm going to cover a few sections from chapter 8 between today and Tuesday. I might have 4 notes here that I get through, and if that happens, then first notes I'll just cover on Tuesday. Let's see how it goes. All right. So you begin with what's called Sturm-Liouville theory, which deals with the certain problems called eigenvalue problems. Now, you've likely seen eigenvalues before in a very different setting, dealing with matrices. The eigenvalue of a matrix and its corresponding eigenvector. But it's any kind of linear operator that can have an eigenvalue and an eigenvector. But when the vector space in question is a function space, as opposed to an ordinary vector space like Rn, instead of calling it an eigenvector, we call it an eigenfunction. So here we're going to learn about basics of eigenvalue problems involving linear differential operators in one space dimension. And that's the beginnings of Sturm-Liouville theory. So what we're interested in are ODEs that have, instead of initial conditions like you're accustomed to from your first ODE class, we have boundary conditions. So you're solving an ODE on some interval, usually a bounded interval like -1 to 1, or it could be like a semi-infinite interval like 0 to infinity. And at each finite endpoint of your domain, you would impose some boundary condition that maybe your solution is equal to some value at that point, or maybe its derivative is. And when you put the ODE together with boundary conditions, we call that a boundary value problem, also abbreviated as BVP, as opposed to an initial value problem. In some cases, the BVP might have a parameter, and there are only certain values of a parameter for which you have a solution of the ODE that also satisfies the boundary conditions. An example of that is an eigenvalue problem, which I'll get into right here. So this is that kind of problem. L is some linear differential operator, and then lambda is some unknown parameter, and we require the solution y of x to be some non-zero function that satisfies this for some value of its parameter lambda and whatever boundary conditions we have. So when that happens, we call lambda an eigenvalue, and the solution y of x that goes with it is called eigenfunction. And to emphasize, we just make it eigenpair. So eigenfunction that is corresponding to the eigenvalue lambda. So we like to create new words prefixed with eigen. So I mentioned that eigenpair would be ordered pair consisting of the eigenvalue and its eigenfunction. So we have all kinds of eigen stuff, I guess. All right. And I'll emphasize the eigenvalue in question could be 0. That's possible. But the eigenfunction must be non-zero. And it can be 0 at a point, but it can't be the 0 function. Because that would trivially satisfy this no matter what value of lambda is. Okay, so here's an example of an eigenvalue problem. So y double prime plus lambda squared y equals 0. So here, in this case, lambda squared is playing the role of the eigenvalue, including the square. or you can think of it as, if I write the ODE this way, Ly equals lambda squared y. So lambda squared is playing the role of the eigenvalue, and in this case, the differential operator involved is minus second derivative. So this ODE is just for rewriting of this one. And we're solving a problem on some bounded interval L, and we have these boundary conditions that the solution must be equal to 0 at both endpoints. So where this can come up, this can describe the oscillation of a vibrating string, where there's no damping involved, so it just vibrate at the same frequency forever. So when you solve a problem, the solution represents the displacement of a string at any given point. So the maximum value deviation of y of x from equilibrium position, that would be the amplitude of a wave. So I call this with displacement at any individual point. But the overall height of the wave, that would be the amplitude. Okay, so now this ODE by itself, we can come up with a solution for this for any value of lambda. The problem is that solution is not necessarily going to satisfy boundary conditions. So when there's no, if you ignore the boundary conditions, you have a set of solutions parameterized by lambda, where lambda comes from a domain that is a continuum, like for instance, all real numbers. Once you include the boundary conditions, especially when it's a bounded interval, then you have a discrete set of solutions. So the set of eigenvalues can still be infinite, but it's a discrete set. For example, it might be something like all the integers, or all the integers times pi. It just depends on the domain you have and the boundary conditions you have. So let's go ahead and solve this problem. If you were to apply the kind of approach that you learned in your first ODE class, you would, from this ODE, get a characteristic equation, which would be like r squared plus lambda squared equals 0. You solve that for r to get the roots of the characteristic equation. And in this case, the roots would be complex. So a general solution of this ODE has this form. So it's a linear combination of cosine lambda x and sine lambda x. In your first ODE class, you would have two initial conditions to satisfy, like y of 0 and y prime of 0 equals something, and you would solve a system of two equations and two unknowns to find the values of the constants a and b. Here, we're going to do something similar. We're going to impose two boundary conditions and get a system of linear equations to solve for a and b. So we go ahead and plug in x equals 0 and x equals L, and we require the result to be 0. So when we plug in x equals 0, cosine of 0 is 1, sine of 0 is 0, so you just get a, but the result has to be 0, so a is 0, there's no cosine term. When we plug in x equals L, we get this. Now we can ignore the cosine term because we already determined that it's gone. And then we have this. This has to be 0. But when is sine equal to 0? It's when the argument is an integer multiple of pi. So the argument to sine here, lambda L, must be some integer k times pi, and that way this boundary condition is satisfied. So you see here that the right boundary condition is the one that limits the workable values of lambda. So now we have a set of solutions. So I'll label y sub k of x is equal to some arbitrary constant, and then sine k pi x over L. So this kind of function satisfies the ODE and satisfies the both boundary conditions where k is an integer. Now here I specified that k must be a positive integer. Well, one thing, if k is 0, the whole thing is 0. So that would not qualify as an eigenfunction. But the reason why we don't consider negative values of k is if I have sine k pi x over L, if I replace k with minus k, that negates the whole function. So, so sine minus k pi x over L is just a negative of sine k pi x over L. We're not linearly independent. So there's no need to consider negative values of k. It would be redundant. We would like to have a linearly independent set of solutions. So that's why we restrict k to positive integers. Now, any scalar multiple of a solution of an eigenfunction is also an eigenfunction. So we could choose a constant b to be anything as long as it's non-zero. There's different things you can do, like we could just set it equal to 1. Another thing you can do is require that the norm of a function is 1. So we use a scalar product, like a typical scalar product being equal to 0 to L, and require that scalar product of yk with itself is equal to 1. So if you substitute this function for f and g into the integral and work it out, and require that the result be equal to 1, then this is the value of b that you get. So square root of 2 over L. So here we have eigenfunctions that are normalized in that sense. They all have a norm of 1, and the eigenvalues that go with them. So recall lambda turned out to be k pi over L, but the original problem had lambda squared, so that's why we square it. And so these functions and these values of lambda squared form a set of solutions to the original problem. Questions about how these solutions were obtained? The eigenvalues turn out to be real. That does not always happen. Eigenvalues are allowed to be complex, but when the operator in question is Hermitian, also known as self-adjoint, probably covered that some time ago, what it means to be self-adjoint, that guarantees that the eigenvalues are real. That's something I'll get into in a moment. It's also worth noting the operator that we used here, the operator L, has is minus second derivative. And so when you take sine, like sine x or sine kx, take a second derivative, multiplying a function by minus k squared. So if your operator is minus second derivative, that operator applied to sine kx gives you k squared, so positive k squared sine kx. So in general, it also has some boundary conditions, but it happens in many cases where the second derivative minus second derivative operator has positive or at least non-negative eigenvalues. Now we're looking more general linear second order differential operator, something of this form. So you have P0 times second derivative, P plus P1 first derivative plus P2. That's strange how many numbered coefficients this way. I would have done like P2, P1, P0, but I want to stay consistent with the text one. So suppose we wanted to find eigenvalues and eigenfunctions of an operator such as this, which is not necessarily easy to do. So we're going to see during the rest of the semester certain operators for which solutions of the eigenvalue problem can be found. You can try using Frobenius' method, for instance, or certain changes of variable. But it's not known how to pull it off in general. Like, there isn't some formula out there for eigenfunctions of any old operator for arbitrary P0, P1, P2. No matter how hard I try to find one. I do, seriously, right, I do tackle the problem of at least trying to find good approximations. So Sturm-Liouville theory refers to, so Liouville, not Louisville. Sturm-Liouville theory refers to studying the eigensystem, if you will, eigenvalues and eigenfunctions together of an operator such as this. So let's suppose that L is Hermitian or self-adjoint. With respect to some scalar product. And y is an eigenfunction, lambda is corresponding eigenvalue. If we look at this scalar product, so scalar product of y with Ly. Well, y is an eigenfunction with eigenvalue lambda, so we just replace Ly with lambda y. Lambda is a scalar, so we pull it out of a scalar product, and you're left with the scalar product of y with itself. Well, that's the norm of y squared. Of course, this part here, we don't know anything about lambda yet, but this part is going to be a positive real number. On the other hand, so we start with the same scalar product, and because L is self-adjoint, I can move the L over to the other y, and the scalar product will keep the same value. I didn't have to put a star here. But but if I then switch the arguments, well, then that means taking the complex conjugate. But now I'm back where I started with a conjugate. So this scalar product, y of Ly, is equal to its own conjugate. Therefore, it must be real number. So because the entire expression is a real number, and the norm of y squared is a real number, the only way that can happen is if lambda is a real number. So in other words, so what has just been shown that the eigenvalues of a Hermitian operator they have to be real. So no imaginary part allowed. Questions about how that was arrived at? Now, given an operator such as this, how do we know if it's Hermitian? We'd have to be able to tell just by looking, or some form of simple check. So we're going to assume that we have boundary conditions imposed at 2 points, x equals a and x equals b, and this will be our scalar product. So standard scalar product on the interval AB. Now, Hermitianness is defined with respect to a particular scalar product. Cauchy is a different one, but we want to see when is L self-adjoint with respect to this scalar product. So I form the expression V scalar product of LU, and see what happens when we use integration by parts. The idea is to express this as, here we have V, scalar product of V, and a differential operator applied to U. I want to express this in terms of a scalar product of U with a differential operator applied to V instead. That involves integration by parts to make that happen. Because the integration by parts will move the differential operator from one function to another. So I break this up into three integrals. Now, what I can do here is coefficient, and we're assuming everything is real here for convenience, but I can move these. I should be more rigorous here and state that assumption. Otherwise, I have to conjugate P0 when moving over here. So, because what happens, whatever functions you have in the scalar product on either side of the bar, they're all multiplied. So I can associate any of these functions with either operator in the scalar product. So, so just shifting P over to the, shifting P1 over to the, and saving P2. Then what I do, with the first two terms, I carry out integration by parts. So, in your integration by parts, you're working with the integral of u dv. So this is playing the role of the u. This is playing the role of the dv, because it's already being differentiated. Always choose dv equal to some derivative, because then you just remove one differentiation to get v. So now I have u times v. Is there a question? So in the integration by parts formula, the role of v is being played by u prime. I guess it's unfortunate choice of notation to use u and v when the integration by parts formula is also normally expressed using u and v. Minus okay. Hold on a second. Okay. I've actually applied integration by parts twice. So this is from a first time boundary terms. You know what? I'm going to include an intermediate step here. There's just too much of a leap from here to here. All right. So if I take this and think of it more really as an integral, since that's what the scalar product is. So from a first application of integration by parts, we're going to have this function times the antiderivative of this one. That's for boundary terms in the integration by parts formula. And then I'll have minus an integral, which is still going to be a scalar product. Okay. Now, if this is from integration by parts formula, u and v. Well, inside here I have to have v into u. Well, v part is going to be this derivative again, so it's just going to be du dx. Not that. Dx. And then I'm going to have the derivative of this. That's going to be 0 conjugate prime. Okay. So this comes from applying integration by parts just once to this. So far I've only covered this. But now I'm going to do exactly the same thing to this term. So wherever you see P0 here, I'll have P1, and then I'm going to have one order differentiation less throughout for U. Okay. So it will be a similar expression. Be very careful how I format this. So here I'll have P1, and then just plain U, and then here also I'll have P1. And instead of du dx, I'll just have U. I'm going to format this the same way later lines. All right, same thing over here. And then this term, I just keep it as is. So from here to here, integration by parts apply to each one of the first two terms. So where it's taken one differentiation operator and shifted from the right operand of the scalar product to the left operand. So we see what happened here. Second derivative and no derivative becomes first and first. Change of sign because of the integration by parts formula. And then here are boundary terms. Okay, now to get from here to here is where I apply integration by parts again, just to this part. So once again, shifting the differentiation operator from U onto P0V. Which again results in a sign change. Minus here becomes plus here. Here are the second set of boundary terms. So we have derivative of P0V playing the role of the U from the integration by parts formula, and then this is the dV. So V in this case is U. This part stays the same, going from here to here. Didn't need to do anything to it. So all the integration by parts is now completed. Now I have a whole collection of boundary terms here, 3 sets of boundary terms in all, and I combine them into one. And then I have 3 scalar products, where in each of them, one of the operands is just plain old u by itself. So using a linearity with scalar product, I can add all the left operands together. So what happens is scalar product of v with LU is equal to scalar product of this operator applied to v with u, but also these boundary terms. Any questions about how this monstrous scalar product worked out? Basically, what we're doing is we're trying to find out what is the adjoint of the original operator L, and then what it will take to make it equal L. And also, what about these boundary terms? Okay, so boundary conditions that we'll assume. Now, there's different choices here. We can assume that they satisfy Dirichlet boundary conditions, where value of functions equals 0 at the boundary points, or Neumann boundary conditions, where the first derivative is equal to 0 at the boundary points. So, if we go here, so as an example, okay. All right. As an example, suppose we assume that if U and B satisfy Dirichlet boundary conditions, then all the boundary terms will go away. But if let's suppose they satisfy Neumann boundary conditions, so U prime or B prime are equal to 0 both endpoints, then these boundary terms will go away. These will go away too, but these not necessarily. So if we want to cover all the bases, the Dirichlet Neumann boundary conditions, we need to have this be 0. In other words, the coefficient of U prime in a differential operator must equal the derivative of the coefficient of U double prime. So as long as that happens, then regardless of boundary conditions, all boundary terms will go away. So if that happens, now if I go back up here, just keep in mind the form of the original operator is this. So P0 second derivative plus P1 first derivative, then P2. Notice the coefficient of the second derivative does not change. It was P0 originally. Here in the adjoint, it's still P0. Now, if P0 prime is equal to P1, then I'll have 2P1 minus P1, and this becomes P1. So then that coefficient doesn't change either. And then finally, if P0 prime is equal to P1, then these terms will cancel, and you're left with P2. So we can also see if the vacuum is satisfied, P0 prime equals P1, this operator reduces to this one. So the condition that we need to make this operator agree with the original, and to make sure the boundary conditions vanish, or at least the two boundary conditions under consideration, is the same. P0 prime equals P1. So V scalar product LU happens to equal scalar product of LV with U. And just remember, when you move L over to the left operand and keep scalar product the same, that requires taking the adjoint. But the adjoint is the same as the original. So this is equal to this by, oh, I forgot the V. Should be a V here. Okay. So this equals this by definition of adjoint. Because this also equals this, and we see these scalar products are the same, except here we have L adjoint, here we have L. L and L adjoint must be equal, so it's self-adjoint. But the boundary conditions played a role in this. Whether an operator is self-adjoint depends not just on what's happening with the coefficients, but also the boundary conditions. Any questions about how we write that L being self-adjoint under this circumstance? When the operator is self-adjoint, the eigenfunctions and eigenvalues have an interesting property. For eigenfunctions in particular. Let's suppose that U and V are both eigenfunctions. The operator L is self-adjoint, and these are the eigenvalues. So lambda U is the eigenvalue corresponding to U, lambda V is the eigenvalue corresponding to V. So now look at the scalar product, VU, LU. But LU is lambda U, just by being an eigenfunction. And lambda U is a scalar, so I pull it out. Then I use the fact that L is self-adjoint to move the L from U over to V. But LV is lambda V times V because V is an eigenfunction. And then lambda V is also scalar, I can pull it out. And I don't have to conjugate it because due to L being self-adjoint, I already know that lambda V is real. So I can pull it out as is. So these are equal. So if I write it this way, everything on one side, I have lambda V minus lambda U times the scalar product U and V must be 0. So what that means is, if the eigenvalues for U and V are distinct, the two eigenfunctions must be orthogonal. That's a very helpful property of self-adjoint operators. Why we like operators to be self-adjoint is because they have orthogonal eigenfunctions. How this is useful is if you what that means is for certain equations where you have a general solution being an eigenfunction, and you want to express the function as an expansion, eigenfunction expansion, and you need the coefficients of that expansion. Well, because the eigenfunctions are orthogonal, then we're able to find the coefficients in that expansion much more easily because you can compute them independently of each other, as we saw very early in the course, where we had we're dealing with expansions of functions in an orthonormal basis. The orthogonality, not necessarily orthonormal, is enough to allow you to compute the coefficients independently. But what if your operator is not self-adjoint? Turns out that it's not hard to transform it into one that is self-adjoint. So here's our eigenvalue problem. So then we're going to scale both sides of the equation by some unknown function w. And that means we're going to get a new operator on the left side. It'll be, instead of L, it's going to be w times L. And because we're multiplying by w on the left, to get the coefficients of a new operator, we're just scaling the old coefficients by w. So here's the coefficient of second derivative, coefficient of first derivative, and coefficient of the no derivative term. So the coefficients, original coefficients, P0, P1, P2, do not define a self-adjoint operator, meaning P0 prime is not equal to P1. What about the scaled coefficients? Is there some magic function W you can multiply by so that the derivative of this is equal to this, which would make L self-adjoint? So in other words, this is a condition that must be satisfied. So the derivative of a new coefficient of a second derivative term must equal the new coefficient of a first derivative term. So I go ahead and carry out the product rule. So I get W prime P0, which I leave on the left side, and then I'll also have W P0 prime, and I'm going to move that to the right side. So now I have this ODE for the unknown function W. Now this is a nice kind of ODE to solve. It's first order in W. It's linear, it's separable. We've seen this kind of ODE before in another situation. So we know what the solution is. So now you write it like this. So really, the best thing to do is I'm going to move P0 to the other side. So the solution is the exponential of the integral of whatever function is multiplying your solution on the right side. So this is one of those good to know solution formulas for this kind of ODE. So this is what we get. Now, this integral we'll have to leave as is. But this one we can work out, because if you make a u substitution, u is equal to p naught, then p0 prime dx is the du. So you get e to the minus du over u. In other words, e to the minus natural log of p0. So this part right here is what you get from actually working out the integral of the second term. But then if I take this minus and move it up here as an exponent, it's e to the natural log of 1 over p0, or p0 to the negative 1 power. The e and the log cancel out, and I get 1 over p0. So now I have my function w that I need to scale by in order to make the operator L, or to get a new operator WL, that is self-adjoint. But let's take a look at what that means in terms of scale of products. So you already have V with my new operator applied to U, and that would be this scalar product, this integral. But then, that would be the same as taking the scalar product of WL applied to V with U. So it would also be equal to this. But another way of looking at it is if I treat W of X not as part of the operator, but rather as a weight function. Because notice we have W of X just as is in both versions of the integral. So instead of thinking in terms of the standard scalar product, what I can say is the original operator L is self-adjoint with respect to this scalar product with the weight function Ws. And what you end up with is so the eigenvalues are real. The eigenfunctions are orthogonal, but with respect to this scalar product. Question about what happened here. What you can do is you can go back to the original ODE that has just had plain old out and solve it by whatever means you choose. For example, Frobenius' method. And the solutions of that ODE are the eigenfunctions for whatever value of lambda you get. And if you know that those eigenfunctions are orthogonal with respect to a known scalar product, you work out what this wave function is, then, as before, you're able to compute expansions in those eigenfunctions efficiently, because at least you have some scalar product in which they're orthogonal. So you can still compute the coefficients independently of one another. It's just that when the original operator is not self-adjoint, you have a little work to do to find out what is the scalar product that will give you that orthogonal.
Dr. Lambers,
Yes.
would you permit kind of a silly question to try to connect something back to the first ODE class? What we just did looks very similar to the process we went through in intro to ODE, where we took a first order linear differential equation and we figured out how to find its integrating factor.
Yeah.
Is that effectively what we've just done here is for a second order linear ODE to identify the integrating factor that will allow it to be solved using something we already know how to do?
Yes. This function here, well, actually, yeah, but this exponential that is exactly that integrating factor.
So would it be possible? I don't want us to do it here in class, but would it be possible to go back and reinterpret then what we did? I don't know what you guys call your first ODE class. MAT, what is it?
Oh, the 285.
285. So would it be possible to go back and reinterpret the linear equation solution technique from MAT 285 as reducing using this self-adjoint business, or is it just not even applicable because it's a different function space?
Well, okay. Because for one thing, in that kind of class, the integrating factor is normally brought up for slightly more general ODE, where you have like your solution, what y prime equals function times y plus another term. Because it's particularly necessary to use the integrating factor to solve an equation like that. And this kind of, because in that case, in that kind of class, you're covering ODEs that are linear, which is what I just mentioned there, when you have like a plus another term, or ODEs that are separable, and then you have this sweet spot when you have both, which is what we have here. And actually, I think that the focus in that class is to be on slightly more difficult problems of each type, like ones that are linear or separable, but not both. Because another way to think in terms of this equation, instead of integrating factor, is if I divide both sides by W, so like W prime over W equals all this. And then I guess the way that you learn how to do it in a class like that is to integrate both sides. And you get natural log of W on the left side, integral of this on the right side, and then you take the exponential.
Oh, I wasn't interpreting that equation as the one whose integrating factor we were finding. I was interpreting the original second order linear equation from above that we are trying to force that one.
Oh, wait. Okay.
Slide down just a little bit more. Down. At the bottom of this page.
Oh, this one.
Yes. So it looks like WX is just an integrating factor for that differential equation.
Oh, I see. Okay. That won't really, that doesn't actually help in the solution of like this problem.
No, that's why I called it kind of a stupid question, because I'm just trying to make a connection, trying to see how a lot of the stuff we're learning in this class is generalization of some things that we've seen before.
Oh, right.
Because I'm pretty stupid, so I like to make connections to things I already know.
Don't do that. I mean, don't call yourself stupid. Definitely try to make connections. So, well, the thing is, in that kind of class, like you're learning certain solution techniques, and in certain senses, we go beyond that here. But in terms of actually finding a solution, compared to what's taught in a class like that, the only thing we picked up is Frobenius' method. As far as like a whole new tool to actually find explicit solutions of ODEs. Whereas the rest of what we've done is like things that you can do with solutions once you find them. So the knowledge of a wave function that will make whatever solution to this you can find orthogonal in some sense has its purpose, but in terms of enabling you to giving you more arrows in your quiver to actually solve this, no. Unfortunately, it doesn't help with that part. So if I were to give you the kind of ODE that wasn't covered in class like Map 285, the only thing we've learned here that will help you solve it is Frobenius's. Or reduction of order to find a second solution if you already have a first one. But reduction of order is something that is covered in our first ODE class. So that's one of the things that's frustrating about working with these kind of DEs is that I've shown a lot of things that can be done with solutions of ODEs that are therefore useless if you can't find solutions. But at least in certain particular cases, we will be able to. But yeah, like trying to make headway on solving an eigenvalue problem such as like the original, like an operator like this, so LU equal Ly equal to lambda y. That's basically my white whale. So that I've been chasing to at least in some general case, at least try to find some way of getting a efficient, approximate solution. But it's quite a challenge. So I don't know if that addressed what you were bringing up, or.
You did.
Oh, okay, all right.
Yeah.
All right. Okay. So here's an example of a non-self-adjoint operator. So x is our p0, and then 1 minus x is our p1, and they do not satisfy this relationship. So that's how we can immediately say the operator is not self-adjoint. So we need to find a wave function that will make it self-adjoint. So all I'm doing here is I'm using a formula for w of x that was derived earlier. So 1 over p0, and the small font's unfortunate, e to the integral of p1 over p0. So I fill in my p0 is x, p1 is 1 minus x. So now I have e to this integral of 1 over x minus 1 once I simplify it. So I have e to the natural log of x from integrating that, and then I have minus x from integrating this part. E to the natural log of x would reduce to x. So the x I get from here cancels with this x. So all I'm left with is this part of the exponent, so e to the minus x. So in other words, e to the minus x is my wave function. So if I were to multiply this operator, the coefficients by e to the minus x, I would find that the result is self-adjoint. At least with respect to the standard scale product. Or another way of looking at it is, if I were to find solutions of this equation, Ly equals lambda y, then I would know that both solutions are orthogonal with respect to this scalar product, where we have a wave function e to the minus x. And what I've done here is I have this boundary condition that my solutions must go to 0 as x goes to infinity. So I'm working on the interval from 0 to infinity. And it turns out that there are known functions that are solutions of this ODE. I don't know offhand how they're found, but my hunch is based on the form of the ODE here, when you have polynomial coefficients, it seems reasonable to use Frobenius' method to at least find one solution of this. If you can find two, great. But if you can only find one, then you can use reduction of order to find another one. And then and those solutions turn out to be polynomials. And so we have a family of orthogonal polynomials called Laguerre polynomials, and they are orthogonal with respect to this scalar product. If you are using Frobenius' method for a problem like this, like what we've seen in examples are you have this recursion relation that expresses certain coefficients in terms of prior coefficients. and generally the result is an infinite series, a power series. But if that recurrence relation happens to result in a coefficient becoming 0, and therefore all subsequent coefficients becoming 0, it's not an infinite series anymore, really. It includes a finite number of terms. In other words, it's a polynomial, assuming that the value of s is an integer, or at least you get non-negative integer powers of x in your solution. So that's what would happen in a case like this, is that you have a what you think will be a power series solution turn out to be a terminating power series solution, and it's just a polynomial. And I mentioned this because there will be at least one homework problem in the future where that sort of thing comes up, where you show, for a certain example, that the power series comes to an end and you end up with a polynomial solution. Unlike, say, Bessel's equation, where it went on forever, it turned out to be an infinite series. So we like when this kind of thing happens, where it stops. Is that the end of the notes? Yes, that's the end of the notes. We have time for the homework questions. I guess we have some answer on Tuesday. And those of you who were not in class on Tuesday, it'd be a good idea to watch the video for that. But any questions that were brought up in relevant. So we'll continue with Sturm-Liouville theory on Tuesday.